Now, good. Now you know how to do the scaling, right? Right. As the device scale, influence from other regions will becomes important, source and drain. Okay. And also influence from long device region, such interconnect becomes important. This is referring to the parasitic resistor and capacitor. Right now you make your transistor so fast, it becomes useless because your interconnect is slow, right? It's just like you have a super fast freeway. But however, at both ends of the freeway, you only have local and a lot of traffic congestion. What's the point of being super fast on the freeway? You still need to wait in the local for a very long time, right? So that is the problem, right? So this is the picture. Right? Let's recall again how the transistor scale, if you look at the Degradation scaling rule, right? For LG, what do you want to do for the gate oxide? So for the gate length, when you scale the transistor, well, how do you scale the channel length? Do you increase or decrease? It's all noise. I think you said decrease. Okay. How about for gate oxide thickness? Do you want to increase or decrease when you scale the transistor?
Decrease.
Decrease. Right? It's all according to the Degradation scaling rule. Okay. How about for substrate doping? Do you want to increase or decrease?
Increase.
Okay. Increase here, actually, you find that is consistent with one thing. When ND increase, it means WD decrease or WM. Because WM is proportional to square root of 1 over QNA or QND, right? So this is consistent, right? So they use different theory, eventually they all comes to the same place, right? So now I'm trying to talk about the scaling challenges. Before we say, when we make transistors smaller, you have short channel effect. We spend a lot of time discussing that, but that is important. Now, what are other challenges that we will see when we follow this scaling rule, right? The first is the threshold voltage. We just say that, right? So we won't repeat. We spend a whole class on that. The other is the so-called subthreshold slope becomes worse, right? Now we will spend some time to clearly, we mentioned one time, this is a very important concept. You need to know that. I'm sure it will appear in the midterm or even final, right? You need to know that. Subthreshold slope, what is that about one more time? If we look at the transistor, now I draw it really large. Let's say this is the metal or poly, right? So this is the gate. And we do have an oxide insulator here, right? To isolate it from the source and drain. And at the same time, we have a depletion layer, right? W, this is just the, I don't call it W, I just call it depletion layer, right? So when you try to change the gate voltage, when you change the gate voltage, what are you really doing? You apply a potential here. And this is nothing but just a capacitor, Cox, right? And then here you also have another capacitor, C depletion, right? I apply a VG here. You try to change this phi S, right? You apply VG to modulate phi S. What does it mean? Look at the band diagram. This was the band diagram cutting from source to drain, right? When I apply the VG, this is phi S. What happened? Phi S reduced, That's what a transistor is about, right? I showed a few times. Any question about this picture? This is the central of the whole class. Any question? Anything unclear? After a transistor is apply the gate bias, I lower the potential at the channel, and then the electron can go over. Any questions? Anything not clear in this picture? Now you see that the phi s does not change with Vg directly, because you remember that I just withdraw this picture. Vg is here, phi s is here, and this is ground, this is C off, this is C depletion, right? So you tell me that d phi s dVg actually equal to C ox divided by CD plus C ox. I won't derive this. This is just a capacitor divider, right? Go back to check the equation, right? This is how it changed. So it means if you increase Vg by 10 millivolt, your phi s does not go up by 10 millivolt. It doesn't. You actually lose something. And that's why we have a bad gate control. Think about, we keep talking about gate control. What if C ox is infinity? This term becomes 1. Then it means whatever I apply to the gate voltage will happen to the surface. I have very good control. Okay? So that's why, let me label it so you later know what I'm talking. Right? So if we define something called N equals to dVg d phi s, then this is equal to 1 plus C depletion divided by C off, right? We want C off much larger than C depletion, correct? When C off is much larger than C depletion, I get 1. That means I changed 10 millivolt at Vg, I got 10 millivolt change in phi s. Okay. Now at subthreshold, we talked about before, right? The transistor cannot be fully turned off because of the fermionic emission. At subthreshold, the current is proportional to a constant times exponential Q phi s divided by kT. And I think you understand why, right? This is because we have a Fermi-Dirac distribution function here, right? And only the electron that is higher than here can go through. If you reduce it, I have more to go through, and this goes up exponentially because this population increases exponentially when you go down. Is that okay? And definitely, this one is just equal to exponential Q Vg divided by nkt, because Vg, right, here we do some, not doing the absolute, we are using absolute value, but it's the same. Vg equal to n phi s, right? So phi s equal to Vg divided by n, okay? Now let's find out what is di dVg. Di dVg, you just do differentiation, you get Q over nkt, and then everything is the same. Am I right? I think this is the not the way that I want to derive actually. Sorry. I'm right about the derivation, but now the question is, if I becomes 10I, okay, then what is the voltage change? Okay, so I do I divided by 10I equals to, I is just I0 exponential QVG1 divided by NKT. 10I is just 10, not 10, sorry. Still I0 exponential QVG2 divided by NKT. Basically, I'm saying that how much VG I need to increase it by 10 times, right? So the VG1 give you I, VG2 give me 2I. For example, here, this is VG1, and then you increase by 10 times. This is VG2, and this is I, this is 10I. Is that okay? Right? If you go through the math, right, you cancel the I and then take log, then you will see that the VG1 minus VG2 minus VG1 equals to NKT over Q, natural log 10. Okay? And by definition, this is the subthreshold slope, because subthreshold slope is that how much voltage you need to change, increase in order to increase the current by 10 times. Is that okay? Any questions so far? Right? So the intuitive concept, right, without any math, is still about how much voltage you need to increase in order to change the current by 10 times. And that is called subthreshold slope, right? For example, at 300 Kelvin, it can be subthreshold slope equal to 60 millivolt per decade. Means that I need to increase this by 60 millivolt in order to increase the current by 10 times. Mathematically, we show that it is NKT over Q natural 10.
I'll just take it.
But what is N? Now you see that N is 1 plus CD over Cox. Why? Yeah, because to increase this by 10 times, I actually need to lower the phi S. But I don't have direct control on phi S. I control phi S through this capacitor divider, which I got a discount, right? It's just that the government took the test from me. I do 10 millivolt, the effect on phi S become only 8 millivolt. So I ask myself, how much voltage gate voltage I need to change in order to change the current by 10 times? It's more than the fundamental physics. It depends on N, which is the technology, which is 1 plus CD over Cox. Any questions?
So the limit of threshold swing is when N is 1? Is that the best?
Yes. Now that's a good question, right? The best is when N equal to 1, traditionally.
And when I just use calculator, that's 16 millivolts, is that right?
That is 60 millivolt per decade. So at room temperature, you can only get 60 millivolt per decade, right? Meaning that you need to increase 60 millivolt in order to increase your current by 10 times. Do I answer your question?
Yes, thank you.
Now, some of you might start thinking, what if I get something less than 1, then I will be famous, right? But unfortunately, someone already did that before, maybe 20 years ago or 10 years ago. They try to find out a way to make this negative. How can you get negative capacitance? And that we are going to discuss the ferroelectric capacitance, negative capacitance. With that, you will get steeper slope than this theory. Okay, we're going to discuss this. But that's why this is so important. Nowadays, device is all about this subthreshold slope. So I hope that you really, really understand this concept from every angle. Okay, and you also see that what if I operate in lower temperature? You will have very steep subthreshold slope. So you see that in our project, I have actually listed a few of the projects just related to subthreshold slope. Ferroelectric, subthreshold slope for cryogenic, right? 2 or 3 projects on that because it's so important. Okay. So let me go ahead, right? Now then, okay, I introduced this subthreshold slope. Now I want to discuss something. Now, when you scale, we keep saying that we want to increase the substrate doping, right? What's the problem of increasing? What's the goal? Why we want to increase substrate doping? Do you remember? We just discussed why we want to increase the substrate doping.
Is it smaller depletion width?
Thank you. Well, you reduce the smaller depletion width. Looks great, right? I should have put this in the last slide, sorry. My cheat sheet is not ordered in the right thing. I cannot write it here. I don't have enough space. Let me write here, right? So this is important, right? 6. When you reduce the doping, when you increase the doping, so as you said, so you try to reduce the depletion width. Then what happened to the depletion capacitance when the depletion width reduce? When you reduce this depletion width, what happened to the depletion capacitance? Depletion capacitance is again the thickness, no, the epsilon of Si divided by the thickness. So what happened to the capacitance? Increase or decrease? It increase. That is really bad. N equal to 1 plus CD divided by C ops is going to increase. And which means that subthreshold slope is going to get worse. Bad. Instead of 16 millivolt, you get 18 millivolt. Okay, you keep scaling, increase the doping, you get 90 millivolt. Your leakage get larger and larger. The benefit is less and less when you try to scale. Okay, this is one problem of scaling. Okay, any questions? Another challenge is band-to-band tunneling. Think about this device. Again, off state. And then you bias it at 5 volts, right? I saturate it, maybe not 5 volts. Let's say 1.2 volts, right? But in the past, maybe 2 volts. And you keep increasing the doping. What will happen? When you increase the doping, you have a steeper gradient. So this is 2 volt at the drain, right? And this is the substrate. So when this one will become narrower when ND increase. Why? Because the depletion width. Can you tell me when you increase the doping, does the depletion width increase or decrease? Decrease.
Decrease.
Yes. Right? If you forget, just think about the PN junction you learned before, right? So as a result, you're going to have so-called band-to-band tunneling, which we discussed before already, right? Because it's narrow. So you have a band-to-band tunneling increase, then the leakage current increase, which is again not good, right? You scale the transistor, you don't do so many stuff. Actually, you want to control the leakage current also. So it counterproductive. Is this clear, this concept? Okay. Another problem is variation. Okay. If you have a very large transistor, right? Let's say if you have a very large country like USA, right? Okay, I say there are 300 million people. Well, or 310 million or 290 million. It's almost the same. The country won't change too much, right? When you change by 100,000. But if you have a small city, right? Let's say Cupertino. If you change the population even by 10,000, it is a big deal. You change a lot. The whole city becomes different, right? It can become empty or too crowded. The whole thing is different. When you make a transistor so small, think about this. If I have only one atom, one dopant, let's say boron, in a 10 nanometer by 10 nanometer by 10 nanometer diameter, and this is almost the right size of today's FinFET. What if you have one dopant? What is the concentration? 1 divided by 10 times the power minus 7 to the power cube, right? 1 nanometer is 10 to the power minus 7 cm, right? So this is how much? 21, right? 10 to the power 21 divided by 3, 10 to the power 18. Right? I think my cheat sheet was wrong. I say it is 21, but this is 18. Now, if I tell you my doping concentration is 10 to the power 18, but then in one fabrication, I have one atom. In another fabrication, I have 2 atoms. Then does it mean that it changed from 10 to the power 18 to 2 to the power 18, 2 times 10 to the power 18? And then from with dopant to no dopant? It does. So it has a lot of problem due to this doping fluctuation. Right? So this is the scale we are playing with. Even one atom make a lot of difference to your transistor. So this is so-called dopant fluctuation. Okay. Another is the gate metal fluctuation. Right? The gate metal may have different grain orientation because it's so small now. Right? Some of the grain are in this direction, some are in this direction. So they have different crystal orientation. As a result, you feel that. Right? It's just like you have in a class, right? If you have equal number of male and female, then you have an overall effect, right? Now, if your class is large, 54 female versus 40 male, it's almost the same as they are equal. But if my class only have 3 people, 2 male with 1 female versus 2 female with 1 male, it's very different gender mixture, right? 67% become 33%. And this is going to affect my transistor consistency. And similarly here, for gate oxide, it's not perfect. We always draw this, right? I didn't draw it well, but in reality, they have fluctuation. Well, if it is large, they FH out. But now when it is small, I really feel this bump. And different transistors have different bump. Again, I have problem. Same for the charge interface. Now I keep saying that we have some trap at the interface. But just look at this doping is the same, where the area is very small. One trap or two trap is going to change your characteristic a lot. Okay. Another thing is, if you look from top, this is source, this is drain, right? I hope that I have a straight line, but nothing is straight, right? Even for your table, you use your magnifying glass and a microscope, it is not straight. Now, if it is so small, you really feel this roughness, edge roughness here. When it is long and wide, I don't care, correct? So why small dimension has worse variability, right? And this is because, right, you start, the quantity, I mean, you can start seeing the variation, or I should say no FH effect, right? You don't have the FH effect anymore, right? Like the class case, while my class population composition is almost the same, whether I have 55 female versus 45 male, and 45 male versus 45 female, 45 female versus 55 male. I can still tell people, oh, it's about 50%, 50-50. But when I'm small, 3 people, right? 3 females versus no male, or 3 male versus no female, the difference is only 3. It's even smaller than the first class I mentioned, but that is a big change. Now I say my class is purely female, and then my other class is purely male, right? So you have this variability, okay? And then why, if you have a higher doping, this Na, I mean N subscript A, substrate doping, that is because the VT, you look at this, VT is proportional to the depletion charge divided by COS, and depletion charge is proportional to Na. If you have a lot of Na, then you have more effect on your VT. If I try not to dope it, then I don't have this variation. Now, this is a problem that we used to have, we don't understand when I was a student, right? You keep thinking, I make the doping smaller, isn't that there will be more statistical effect, right? Because now in the past, maybe I have 10 atoms, now I only have 1 atom. Isn't that plus minus 1 atom, you have more effect? But no, it's because we're talking about the VT. When you only have 1 atom, your effect on VT is small. So you don't contribute to the variation. So, okay. Any questions? Now here shows the simulation of the dopant fluctuation, right? You see that if you try to convert the atom to doping concentration, it's not constant in the channel. Or even you can see in individual atom in the channel. And if you try to measure the IDVG curve, this is exactly the same device, right? But take dopant fluctuation into account, it changes a lot. And then eventually your delay will change, your circuit change by more than 25%. You don't want that. Okay. The last scaling challenge is the gate tunneling. This is the gate, right? Gate oxide. When it is so thin, we say we want to reduce T-ox, right? When it's so thin, you can have the tunneling. The first thing is the so-called Fowler-Norheim tunneling. This is because originally it is a square, it's a rectangle, but the field makes it triangle. Right? Then you have a lot of more tunneling. This is field enhanced tunneling. Because do you remember I am talking about tunneling? It's somehow related to the area about your energy. Triangle, you have more area. With electric field, it becomes a triangle. I mean, rectangular will have more area, right? Originally, it was rectangle, but when you apply the field, it becomes triangle. Area smaller, more tunneling. Well, but nowadays, even not this. This was used in the flash memory for your device, not for no high tunnel. It uses a lot in your memory, your thumb drive, right? Now we talk about direct tunneling because it's so thin. I even don't care about the field. It's just very thin, right? Very thin, right? So even rectangular barrier has tunneling. So what's the problem of this? You increase the gate current, right? Tunneling increase the gate leakage, right? And even more, we have this type of, if you have a polysilicon, you can tunnel from conduction band to valence band to conduction band, valence band to conduction band, or hole from valence band to conduction band, right? So what is the problem? The problem is very simple. If this is off, right, this is a circuit, and you store the charge here, okay? Now because of tunneling, they will leak away. This is something called latch, right? I don't know if you learned about that. But the problem is, if you have gate tunneling, even they are off, you still have the current lead away. Then you change the information you store. Any questions about this? Now, finally, I'm trying to show you something called roadmap for device and system, right? So this is 2017. Every year, I try to publish the projection. Okay, my connection was not good, right? I just ask you if you have any questions on this. If not, I show you something called International Roadmap of Device and System. You can download from the internet. Every year it publish, right? It tell you at each year how the transistors should scale. And you give a name of the node number, 10 nanometer, 7 nanometer, 5 nanometer, 3 nanometer. But the gate length is different. You see, 20 nanometer, 18 nanometer, and even later, you just keep constant, 12, 12, 12 for all this technology node. But it's difficult. In 2020, this year, they published a new one. You see that now they actually make the gate length longer for this 5 nanometer technology node, 20 and 18, right? This is high density, this is high performance. It's longer than what they projected before. It's so difficult to scale. On the other hand, it also means that it's not necessary to scale because you have other parasitic issues. The red one means that they still don't know how to do it. So for 12 nanometer, they still don't have the idea how to make the 12 nanometer transistor gate length works well. Okay. Any questions on this IRDS roadmap, international roadmap? So in the future, we cannot just rely on this so-called more, keep scaling. We talk about, this is for device and system, we talk about beyond CMOS, ferroelectric, what we just talked, right? Don't just, So do you have question? I cannot hear.
Your connection, you were breaking up while you were talking.
Oh, my connection was breaking. Okay.
Yes.
Okay. Yeah, but basically this is, I'm not going to repeat, but basically what I'm trying to tell you that you have this IRDS, and besides CMOS, you want to go beyond CMOS, new material, 2D material, ferroelectric, etc. Okay, or emerging research material, cryogenic and quantum information processing. Right? So we are all exploring the new paradigm, right? So that's why I want to talk about scaling. I spend a lot of time, but I think that is okay. We have plenty of time, because actually now I'm thinking for your project report, because we have too many people, maybe for the last 2 class, I will not ask you to present. I might ask you to record a video, right? A few minutes, and everyone look into that. And then we have those to continue to cover the materials. Okay. Any question about scaling now? Here are some appendix for 2-region model. No need to study, but if you are interested, I include for your information. No need to study, no need to study, no need to study, no need to study, no need to study. And then we will start talking about silicon on insulator. This is what you need to study. This is a new topic. Okay, so before I continue, any questions on the scaling?